cold, right? All right, everyone. We're getting close to the end. How has this week been doing for you? So the PDE class will start today?
Yes.
Go and check it out. I think you guys will like it. No problem. Just our viewers on YouTube, they complain. So this is lecture 19. And I want to talk to you a little bit about the Fourier Transform. Okay, good. Let's see how we're going to do this. So these last two lectures, after we have seen a little bit about Hilbert spaces last week, I want to conclude this course with perhaps talking to you a little bit about Fourier Transform and if I have time about Fourier Series. Okay, so this is a very nice object that comes into play not only in analysis but in many different neighboring areas like partial differential equations, probability, dynamical systems, number theory, for example. It's a very powerful tool, and say the main purpose of this is to understand a little bit about oscillatory phenomena in nature, right? You want to somehow quantify and qualify different sorts of oscillations. So once a person asked me, what is the definition of harmonic analysis or Fourier analysis? And somebody told me that it was just the art of estimating an integral without passing the absolute value inside. So you really want to understand cancellation, how cancellation and oscillation takes place, and you want to make and take advantage of this. Okay? So Fourier, back in the late 1700s, beginning of the 1800s, he was a French mathematician. They were like, he had this very nice idea of constructing this operator, and it serves, let's say, just two basic purposes. One of them is to have this idea to express a function as a sum of more elementary functions. So when we talk about Fourier series and we want to express a periodic function as a sum of sines or sum of cosines, so this basic idea has been present in mathematics for a long, long time ago, and it will keep being present for long years to come. The idea to express an object in terms of more elementary objects that you understand a little bit better. Right? So this is the idea behind the Fourier series. And another advantage of these things, as we'll see, is that we will construct an operator that will essentially transform differentiation on one side into multiplication by polynomials on the other side. And this sort of tool is very important to solve partial differential equations or differential equations in general. Okay, so this was very well received at the time. If you go to Paris, you have the chance to go to Paris, I'm sure. In the Eiffel Tower, if you see the Eiffel Tower, they do something very nice. They have the names of the scientists around the Eiffel Tower. And you'll see names like Poisson and Fourier there. You can take a picture. All right. So the setup is this. We will start with a function. Let's just call it, for a second, the basic properties. So I will start with a function in L1 of Rd. Okay, an integrable function in Rd. And I will define f hat, the Fourier transform, at a point, let's say y, will be just the integral over Rd of e to the minus 2 pi I x y f of x dx. Okay, So from now on, this is the Fourier transform of the function f. Okay, so this is what we call Fourier transform. If you go, there is a little bit of a choice here. If you go to many books, you will see potential variations of this. And here, some authors put the 2 pi, some authors don't. They prefer to put just I, x, y. Some authors just put with the plus or with the minus, and some authors divide by a certain constant here, 1 to the 2 pi raised to some dimensional thing. So there's some variations, but the object is the same. You will take your function and you will integrate against the kernel that oscillates. Okay, so recall that e to the, minus 2 pi I xy is just cosine of this number, minus 2 pi xy plus I sine of minus 2 pi xy. So this is a complex number of modulus 1 that kind of oscillates. Right? So there's a lot of cancellation going on in this integral. If your y gets very, very big, so you see that this will oscillate even faster. This is an integral in x. And we want to understand a little bit better the properties of this integral. So why am I assuming that f is in L1? So that this integral makes sense. Nobody questions the definition, right? So this is an integrable function. I integrate with whatever number here I want because this has absolute value 1. So this is absolutely integrable. It is a number, and I'm just calling f at 1. Okay, now let's see some basic properties of this object. And I'm going to list some basic properties here and let you prove as an exercise because they're really simple. So just a little bit about notation. Let me just maybe throughout the next 2 lectures, I want to say we have defined this operator translation. I'm going to say the translation by a vector y of a function f of x is just by definition the f of x minus y. Okay, so I'm going to denote the translation by y like this. If I have, say, a vector x, so if alpha, alpha 1, alpha 2, alpha n, where all alpha i's are integers bigger or equal than 0, this is called a multi-index. Okay, and I'm going to say that the size of alpha is just the sum of the sizes of this alpha i's. Let me call it D. So I'm going to, dimension for us is going to be D here. Right. So when I write a vector x in RD to the multi-index alpha, what I mean is just x1 to the alpha 1, xd to the alpha d. And when I write partial differential with respect to the multi-index alpha, I mean just d dx1 alpha 1, blah, 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 d dx d alpha. Okay, so this is taking alpha 1 derivatives in the first variable, alpha d derivatives in the d variable. If I am in RD, right? So here, x is a vector in RD. All right? Okay, so with this notation, following properties hold. So let me call this proposition 1. These are just some basic properties. Okay. Let f and g be functions in L1 of Harmonic. Then, first one. An infinity norm of f hat loses to the L1 of f. 2. The Fourier transform of the translated function at the point c is just e to the minus 2 pi I x c. Let me call it 3. And let's see, tau eta of Fourier transform is equal to h hat, where h of x is just e to the 2 pi I x eta of x. It's good. 3. Let me write this. So if t is an invertible linear map on R D and S is T transpose inverse, then I'm gonna say that Fourier transform of f composed with T is just the inverse of the determinant of T f hat composed with f s. In particular, if T is a rotation, and f composed with T Fourier transform is just f hat composed with T, and if T is the dilation, let's say T minus 1 x, 0, let's say Tx, then Fourier transform is just 1 over T to the D f hat over x equal T. Good. 4. Fourier transform of the convolution is just the product of the Fourier transforms. 5. If x to the alpha times f belongs to L1 for any multi-index alpha less than or equal to k, and f hat belongs to ck of Rd, and the partial derivative alpha of f hat was just this thing, minus 2 pi I x to the alpha f hat. Yes. What else? Final property. Let's see if I can squeeze it here. If f is a function which is ck of Rd, d alpha of f belongs to L1 of Rd for alpha less than or equal to k, and d alpha of f belongs to C0 of Rd, and I have to go to this side, otherwise you won't see. this is for alpha less than or equal to k minus 1. And Fourier transform this guy is equal to 2 pi I c alpha f c. Okay. So I'm listing to you six basic properties of the Fourier transform. Just one little note. I'm using here CK is the usual space of functions that have, there are continuous, that have k derivatives, and the kth derivative is continuous. And I'm using here the space C0 with the 0 on the bottom to mean the continuous functions that go to 0 at infinity. Okay, so C0 of Rd, this is the space of continuous functions that go to 0 or that vanish at infinity. It doesn't mean that they are 0. It doesn't mean that they have compact support. Right? That is, you know, for any epsilon bigger than 0, there exists a compact k such that f of x is less than epsilon if x is outside of k. Okay, so they go to 0 at infinity. This space I'm going to call C0 of Rd. It will play an important role in what follows. Continuous functions that go to 0 at infinity, or that vanish at infinity. Okay? Again, they do not have to have necessarily compact support, and they, of course, they do not have to be integrable. They just go to 0. They can be going to 0 very slowly or very fast. Like a Gaussian is here, exponential function is here, anyone else that many other functions. Okay, so I want to highlight two. Let me just comment. I really strongly suggest that you just take all of these basic properties and do this as an exercise. Okay? I won't be assigning any more homework in this course for you to deliver back to me. I'm okay with the homeworks that I collected, and I know that you're busy with the other courses and exams, but I will just assign perhaps next Friday a final, let's say, homework, basic as some suggested problems for you to think about before your exam. You don't have to deliver back to me. This is problem number 1. Okay? Prove all these properties. Let me just comment a few of them, because I am actually describing different phenomena here. So the first property, okay, I will just comment on some of them. First of them is very important, right? So the first of them is just says that f hat of c, by definition, is just the integral over Rd over e to the minus 2 pi I x c f of x dx, right? If I take just, this is the non-harmonic analysis way of estimating things. If I just want to say absolute value of f of c, it's just less than or equal than the absolute value of this, and I just move the absolute value inside, right? Just moving the absolute value inside, what you get, of course, is the L1 over f. This is the most trivial way of you to doing an estimate on an integral. Just move the absolute value inside. Okay? This should be what you always do first. Of course, we want to do better than this, right? But at least this we can do. So if your function is integrable, you have to be able to tell me that the Fourier transform is bounded. And an infinity bound, it always loses to the L1 norm of f. Very basic, all right? Second, okay, so this is actually proved. The Fourier transform has this right interplay between translation on one side and what we call modulation on the other side. So modulation is just multiplication by a character, an exponential like this. So it takes translation on one side a modulation to the other side. Right? Sometimes when people work with the Fourier transform, they will refer to as the, I don't know, physical space and the Fourier space, or physical space and the frequency space. So they have different names for the space where F is acting, the space where F hat is acting. You know, so this, whatever name you prefer, let's just call it physical space and frequency space. It will take translation on one space into modulation on the other side. Okay, so yeah, the board is too small. This is again not very hard to do, right? So if you start, we'll just start with 2. So if you want to try to prove this one, for example, what's the Fourier transform of this function? So you want just translation by y of the function f hat at the point c. Well, you just do the definition. This is the integral over Rd of e to the minus 2 pi I x y xc, and then whatever function you're taking the Fourier transform here, t y f of x dx. Right? This is just the definition. Now, the definition of this function, tau yf at the point x, you know what it is. So this is the function f of x minus y. Y here is a fixed vector. Now it's just a matter of changing the variables here. You just call x minus y z. So this integral keeps being on Rd, and then e to the minus 2 pi I x. So x then became z plus y, c, f of z dz. And then there is you're integrating z, there is a certain constant factor here that does not depend on z, right? Which is the e to the minus 2 pi I y c. And then the rest is the e to the minus 2 pi I z c, f of z dz, which is just f of x. This is the first expression. So translation by y. And then, again, here, you gotta be careful how you define translation. You see in books, they will define translation by y as f of x plus y sometimes, or x minus y. But define this way, if you define translation this way, this will take the modulation with the minus sign here, the minus 2 pi I y. I suggest you don't memorize these things. It's just, I never memorize these things because if you see it in the literature, you see the definition of the Fourier transform with the plus, with the minus, and the translation. Just write it down and remember in 30 seconds what it is. Okay? And the same thing, I mean, if you want to do on the other way around, so if you want to just take the translation by vector eta of your Fourier transform, this is the Fourier transform of a function h, which is the original f modulated by this eta parameter here. It's just the other way around here. Proof is essentially the same. Okay, so take translations into modulations on both sides. The third expression here actually tells me what happens when I compose with a linear map. Okay? And again, it's just a matter of plugging into the definition and changing variables. Okay, so just plug in the definition. This will be f of tx, and then you just call txz. Change the variables. This is the Jacobian that appears, and this is what happens. You have the inverse of the transpose coming up in this inner product here. So when you do the inner product of x, ty, it's going to be something like, if you want to revert this, it will appear t to the minus 1 transpose of x. Yeah. In particular, I call your attention that if you have a rotation, then you have properties like this whole, right? That they keep the inner product. Then if t is a rotation, then, f composed with the rotation hat is just like f composed with t. And if t is the dilation.
It's exactly the same. The one before, the determinant of the rotation is plus minus 1.
Well, this is just a modulus of determinant, right?
It is plus or minus
Yeah. Okay. Yeah. And what am I doing now?
Did they have in the last PC on F or?
The last one is a translation, or is a dilation, right? So if your linear transformation is just multiplication by t, the Fourier transform will just take the form 1 over t to the d, this is the dimension, and I've had c to the t. I let you work on this thing, maybe if I've done something wrong here, you tell me.
Doesn't this look like the thing we use for approximation of identity?
It resembles, yes. It resembles very much. Yes. You will see that the approximations of the identity will pop up here soon. Okay? Okay, so this is just work this. This is just a change of variable. Fourth property, very nice. The Fourier transform takes convolution into product. Okay, so it takes convolution into product. And also the proof of this is not hard. Be aware that we are already using some of our tools. Say, for now I have just told you how to take the Fourier transform of integrable functions. Okay, so the first thing that when you look at this, and if I take f in L1 and g in L1, the convolution of f with g is in L1. This is perhaps basic fact of Young's inequality, if you want. Okay. Right? So this function is a function in L1, so hence you can take the Fourier transform of this guy, and this is just going to be the product on the other side. The proof is simple, right? So one is f convolved with g at a point c. Well, again, just by definition, this is e to the minus 2 pi I x c, f convolved with g at the point x dx. Now you go in and let's open this up. So what is f convolved with g at the point x? It's just the integral over Rd of f of y, g of x minus y dy dx. Okay? Now you have integration in x and y, these two variables. Whatever is inside the integral is absolutely convergent. Right? It's absolutely convergent. If you put the modulus here, kill this by 1, you have just the integral of f and the integral of g, and they're both integrable. So if whatever is inside the integral is absolutely integrable, you can change the integrals as you please. This is Fubini's theorem. Whenever you want to change integrals, if whatever is inside is absolutely integrable, you can just change as you please. So here, I mean, you don't even have to change, but the idea is just to write this xc here as, so you have the integral of Rd as e to the minus 2 pi I. You write it with yc, and then you write it with f of y, and then you write e to the minus 2 pi I, let's say x minus yc, g of x minus y. Well, I guess you have to do the integration of x first, and then y. This is what you want to do. Now, when you do the integration on x for this guy, you may change the variable x minus y to a z. What you get is just, this is going to be the g hat at the point c, and the other integral will just be f hat at the point c. Okay, so it transforms convolution into product. So you see at the end, now maybe we should make a little comment here. At the end, the Fourier transform f, if you please, will be a linear map. Right, so we're building a linear map. It will be later on linear map from L2 to L2. We're going to prove that. linear, meaning that if you have a plus here, it will take into a plus on the other side. But you have also a structure of an algebra in this space, right? So if I actually want, so I'm mapping L1 to L infinity for now. It's a vector, it's a linear transformation. But if I consider L1 as an algebra, if I put another operation, so I have the structure of a vector space, so I can multiply by a scalar, and I can add two vectors, but I could also consider this L1 with the sum and the convolution. So convolution acts like a second operation in L1. If I take convolution of two functions in L1, it will be another function in L1. And it's associative with respect to the operation of addition here. So this is like an algebra. And this will map into L infinity with the operations of addition and pointwise multiplication. So this is nice. It preserves the two operations, the plus, and sends the convolution into the multiplication on the other side. Good. Algebra homomorphism. You guys that know algebra, tell me if I have the right terminology. Good. So this is okay, very important, takes convolution into product. Now, so this is nice. Translation and modulation are pairs of operations that happen together. Convolution and product, again, one side convolution, the other side becomes a product. This is the action of a linear transformation. And this is an important thing for solving differential equations. It will take multiplication by polynomials on one side into differentiation in the other side. If your function has some decay, so this, look what this means. If x to the alpha times f is integrable, so this means that, well, for f to belong to L1, for f to be integrable to start with, means that it has some decay. Now I'm saying if you even multiply by a power of x, so when x is big, this is big. So if x to the alpha times f is still in L1, so if f actually decays fast, then your Fourier transform will be a smooth function. We have k derivatives. So you have to have this in mind. Decay on one side means smoothness on the other side. So if your function decays fast, on the other side, the Fourier transform will be very smooth. And vice versa. If on one side the function is very smooth, on the physical side the function will decay fast. It's not surprising that if you take a Gaussian, for example, if you multiply the Gaussian by any polynomial, it will still decay. It will still be in L1. So the Fourier transform of a Gaussian is going to be a smooth function, as smooth as you want. It will be a infinity function for this result, because this will hold for any k. In fact, we shall prove that the Fourier transform of a Gaussian is a Gaussian itself. So this is, of course, in accordance with this. And let's see. Let's try to prove this property. So if x to the alpha is in L1, again, x is a vector in Rd, and alpha is a multi-index in Rd, so x to the alpha actually means that I multiply by x1 to alpha 1, x2 to alpha 2, and so on. Then f hat is in ck. Let's just see how I will take one derivative. So you say that your f hat of c is just integral over Rd, this is property 5, of e to the minus 2 pi I x c.
I'm just confused here. When we say for modulus of alpha less than k, for any k, or what is k exactly?
For some k. So if x to the alpha f in L1 for let's say for any alpha less than a certain k, then f hat belongs to ck, and the Fourier transform of this is just okay. Maybe I should have said that, but I hope it's clear from the context that x is a vector in Rd, and of course my function is a function in Rd. Okay, so for it, I start in L1 of Rd, and I map into another function of d variables. X times c is, of course, here the inner product of Rd, okay? So, suppose you want to take one derivative here. Suppose you want to take one derivative here of this guy. Right? You want to know if the derivative in the direction of let's say, on the first variable exists. So you would take the limit, very brief, limit of h goes to 0 of f hat of c plus h times e1, let's say this is the first coordinate, minus fc of a, c, and divide by h. Here inside you would do the same. So it's just the integral of rd. Well, you put this guy here, this guy there. So this will be e to the minus 2 pi I, and then x c plus h e1 minus e to the minus 2 pi I x c, this thing over h. And f of x dx. Okay. I want to argue that I can send a limit when h goes to 0. Okay, this is an equality. Now let's see what happens when h goes to 0 in this integral. Okay? I have f, which is integrable. What I want to show is find, say, a bound for this guy. Now we do have some sort of,
I think we can reverse it to have f minus the difference becoming f. Not
this is a mean value theorem. What do you know from mean value theorem? This is just the derivative of this function at a certain point in between, right? So what's the derivative of this function? So I'm fixing my, well, what's the derivative of this function here in the variable c? E to the minus 2 pi I x c. What's the derivative of this function here? So the derivative g prime of, well, the derivative in the first coordinate, d dx1, right? dxc is just e, it's just minus 2 pi I x1. It's 2 pi I xc. Okay? So what I'm telling you is that
an estimated
But
difference.
the theorem is not still true in complex analysis for this part.
well,
Is it, yes, there is some generalization in complex analysis, but not.
I want to say, let's see. This is the derivative of this guy. You would use the mean value inequality in complex analysis, right? This is less than the supremum of the derivative connecting these 2 points. So all that I want to say, or you could just take the real part and the imaginary part if you want. That works fine as well, right? So this would be the derivative in this direction. Am I right? Yes. So yeah, I mean this is the, so when you go from this point, say c plus h e1, well, I am actually looking at the function. So if I say for any fixed x, if I fix my x here, right, I'm actually looking at a function from Rd to C. It's a complex valued function. This is what this is. Right? My x is fixed. And I just go from one point, C, to this other point. I have a mean value inequality. Right? This loses to the supremum of the derivative in say, the straight line that connects this point to this point. But this is the derivative of this function. This always has absolute value 1 in the curve. So my claim to you is just that this object here loses in absolute value to, whatever it is here, loses just to this guy, minus 2 pi I xi, say, in modulus. Okay? So this is dominated by this quantity. Okay. Now, since x to the, well, alpha here would be just the, I'm just assuming, trying to take one derivative with respect to E1. So this is alpha is just alpha 1 equals 1 and the other is 0. So since I'm saying that x1, since x1 times f belongs to L1, this is the hypothesis, this guy here, for any h, is dominated by this function, which is an integral function. Therefore, I can use the dominated convergence theorem to send h to 0. Okay? When I use the dominated convergence, that's the catch. So all I'm trying to say is, I'm just trying to justify the use of the dominated convergence. Okay? So you would come from this, you would come here. So by dominated convergence, the right-hand side would converge when h goes to 0 to the limit, to the integral of the limit here. But this is a differentiable function. When h goes to 0, you know what the derivative is. It's just minus 2 pi I x1 times e to the minus 2 pi I x c f of x dx. Or if you actually want, you should just put this close to the function, which is more enlightening. E to the minus 2 pi I x c and then minus 2 pi I x 1. Okay? So this converges to this thing. Well, but if this limit when h goes to 0 exists and it's a number, so this is the definition that this function f hat is differentiable in this direction. So this is actually df hat d, let's say, c1. Or in our notation, let's say d, say alpha 1. Well, no way. Okay, taking one derivative here was just moving down minus 2 pi I x 1 on the other side. Okay, so I took one derivative in one coordinate. If I took another derivative in another coordinate, I would move another guy down. So this is why, you know, let me see. So if this guy has alpha derivatives in different multi-indices, then for any alpha less than k, I could play this game and prove that f hat belongs to ck, k times differentiable, and the derivative alpha f hat is just this minus 2 pi I x raised to this multi-index alpha, where you want to understand this is minus 2 pi I x1 to the alpha 1, minus 2 pi I x2 to the alpha 2, and so on. Just the Fourier transform of this here. Fourier transform kernel of a function. This is the Fourier transform of this function. Okay. So this is essentially number 5. And number 6 tells you the opposite. So if your function has smoothness, the Fourier transform has some sort of decay. So if your function is ck, and then if all the derivatives are in L1, and the derivatives go to 0 at infinity for k up to k minus 1. So the derivatives are integrable up to k, and they go to 0 at infinity up to k minus 1. Then the Fourier transform on the other side, you know, the Fourier transform of the derivative is just 2 pi x c alpha f hat. And the reason, I can just try to prove this, you'll play the same game, but now instead of taking derivatives on one side, moving the derivative inside, what you want to do is just integration by parts. So you will do integration by parts, and this fact here, that it goes to 0 at infinity up to k minus 1, will just make the boundary terms vanish. So you'll do integration by parts k times. Okay? So this is just integration by parts. Good. Okay, so this is just an overview of this proposition of the basic properties of the Fourier transform. But please sit down and work them out, work it out, everything. The relation between translation and modulation. the linear transformation that transforms convolution into product, and then this relation between multiplication on one side with differentiation on the other side. Is that clear? Okay, let's move on to more interesting stuff. Let's see. Okay. What I want to do now is perhaps to give you the first nice result of this. So this is called the Riemann-Lebesgue lemma. Once you understood what the Fourier transform is, and you saw the basic properties were just easy manipulations of things, if f belongs to L1 of Rb, then the Fourier transform belongs to C0 of Rb. So I'm going to tell you a little bit more about where it maps to. Okay. So the Fourier transform, we have already seen that it's a bounded function. Now I'm telling you a little bit more. No, it's not only a bounded function, but it's a continuous function, and it goes to 0 at infinity. So this is very, very nice. So this starts to capture a little bit of the oscillation that I told you, right? So f. So never feel confused. Just write on the board the definition. So if f is integrable, we have to verify two things. That this function f hat is continuous, and that it goes to 0 at infinity. So when c goes to infinity, and c goes to infinity, the reasoning behind here, if c is very big, this kernel, which has c x times c, will oscillate really, really fast. Even when x is small, it will already oscillate really fast. X is like 1,000,000. So this means that things will oscillate, and inside the integral things will cancel very fast, making the integral very small. So this result here already understands a bit more about the decay on this side. Okay? Saying that f hat was a bounded function was very trivial, just moving the integral inside. I'm saying, okay, it's not only a bounded function, it's a continuous function, and it goes to 0 at infinity. There's a minus, yes, thank you. Right? Anyway, so when we review these notes, if I've done something, if I've written something on the board, might be a typo here and there, that's okay. More important is to understand the philosophy of things, not the details. All right. You see, a lot of things that we will do today and Friday already builds upon things that you have learned in this class. Proving that such a function is continuous in the variable c. This is, again, dominated convergence theorem. So you have to understand what is f hat of c plus c1 minus f hat of c. Right? When c1 tends to 0. So this is what you have to understand. Oh, let me just put in the formula. E to the minus 2 pi I c plus c1 minus e to the minus 2 pi I xc. And I want to use dominated convergence. And I can use dominated convergence because whatever is here is just bounded by 2. This number is bounded by 1, this number is bounded by 1, this is bounded by 2, this is integrable, so this is dominated by 2 times the absolute value of f. I can just move my limit inside. The limit when c1 goes to 0, the limit when c1 goes to 0, this will give me 0 at the limit. Okay? So continuity is just a very elementary application of dominated convergence. This implies continuity. Okay, now let's prove that it goes to 0 at infinity. This is a very good result. Now, let us prove, and you tell me how to do it, that f hat of c goes to 0 as c goes to infinity. How would you do that?
First, we can prove by step functions and come back support step functions and so continuous and
Okay, so this is a little bit, this is a very, very typical argument in analysis. By now, you should be a little bit more comfortable with this sort of argument. I want to prove that f hat of c goes to 0 as c goes to infinity for any L1 function. Bottom line is that you should not start with any L1 function. Try to work on a dense subset. What is a good dense subset of L1? Functions of compact support, maybe, but the compact support might be very crazy, right? What would be an even simpler set? The simple functions, the characteristic functions of sets. The set might be very, very crazy, but just characteristic functions of cubes. Characteristic function of rectangles. Right? So the idea is to actually, but you have seen how the Fourier transform behaves under a linear transformation. So we already know that the characteristic functions of rectangles, the linear combination of characteristic functions of rectangles, is dense in this thing. But if I can just work with actual cubes, if I can prove for the characteristic function of a cube, then I could just take a linear transformation and transform the cube into any rectangle that I want, right? And the Fourier transform behaves okay with linear transformations. It won't change. If this behavior is okay for the characteristic function of a cube, it will be okay for the characteristic function of a rectangle as well. Even if I have a cube and then you can just dilate, because we already know how the Fourier transform dilates, I can actually work with just one cube, the unit cube. So you see, there's magic on this thing. You don't have to prove this for all L1 functions. You just have to prove for the characteristic function of the unit cube. And that's it. Okay? Okay, so we just have to prove it for the characteristic function of the cube. Let's say, but the cube C being, I don't know, minus 1y to the d. And I'll say it again. If we prove the result for characteristic function of the cube, saying that the Fourier transform goes to 0 when c goes to infinity, then by dilation it holds for any cube, right? By dilations and translations, if you want, it holds for any rectangle, actually. You can translate in one dilate in one variable differently than the other. By linear transformations, it holds for any rectangle. And then you can take linear combinations. You can take linear combinations of these things. Sum over 8k x of rectangle k. Okay? So if you take a function which is a linear combination, a finite linear combination of characteristic functions of rectangles, the Fourier transform is obviously a linear operator from the definition. It's a linear operator. So the Fourier transform of this function f will just be f hat of sum over ak is then the characteristic function of rectangles k. Now, if each of these guys goes to 0 at infinity, meaning if for each k, if you give me epsilon, for each k there's a huge compact such that it's less than epsilon outside that compact, you just take the biggest of these compacts and then it will be less than epsilon times this n, which is fixed, outside this compact set. So if each of these go to 0 at infinity, any linear combination of functions in this space, it's obviously there as well. Right? And then, of course, you're going to use that this is dense. Okay? So the idea is now, for general f in L1, general f in L1 of Rd, given epsilon bigger than 0, we can choose a certain g, which is just a finite sum of characteristics of rectangles with g minus f in L1 less than, say, epsilon over 2. Once you have chosen g, so once g is chosen, we can choose a compact k such that g hat of c is less than epsilon over 2 for c in the complement of k. If I know how to prove it for these functions. Hence, now it's just a matter of using f hat of c is just g hat of c plus f minus g hat of c. This is then less than or equal to g hat of c plus the L infinity norm of f minus g hat. This is less than epsilon over 2, and this is less than the L1 norm of g, f minus g. This is, if you want, so this keeps this. Now, so this holds in general. This is just equal to this, so the absolute value is equal to the absolute value of this. I just now use the triangle inequality, so this loses to g hat of c plus the f minus g hat of c. Now I'm using the L infinity norm. This loses to the L infinity norm of f minus g, which loses to the L1 norm of f minus g. Now, if you are now for c outside this compact k, this g hat here will lose to epsilon over 2, and this guy by construction, we made it to lose epsilon over 2. So this is epsilon. So you end up proving that f hat of c loses to epsilon outside this same compact k. Okay? This is a very nice example of a standard approximation argumental analysis. You see? Instead of proving for all functions in L1, you just have to prove for one function, the characteristic function of the unit group. But then you have to work it. Now this is, once you're very familiar with these arguments and you see a problem like this in your lives, this should be done in 30 seconds in your mind. Say, okay, I just need to prove, okay, this problem is just equivalent to proving for this function. And then you start working. Good. So how do we prove it for the characteristic function of the cube? Now you just compute it, right? So if your function f of x is just the characteristic function of the unit cube, let's just say the cube. And here's up to you. You can even put the cube, say minus half, just so it has side 1 or yeah, let's just put minus half. Let's just put this cube of side 1 centered at the origin, right? So let's write what this is. F hat of c. It's just the integral over the cube minus half e to the minus 2 pi I x c, and then the characteristic, the function is 1, right? So this is just Now, the nice thing is that this integral here breaks into a product of integrals. So this is just a product from j, from 1 to dimension d, of the integral from minus half to half of e to the minus 2 pi I xj cj dxj. Okay? And then you just complete this integral. And you find that this is the product, j1 to d. The Fourier transform of the characteristic function of the interval minus half. This is what you're doing here. Fourier transform of the So, if you had realized that the integral breaks this product into the product of integrals, all you have to do is compute in one dimension the Fourier transform of the characteristic function of an interval. Let's just say minus half. This is just sine pi x over pi x. If you just do the computations. This is just the integral of an exponential. So this is just this guy. And obviously, sine pi x over pi x is a function that goes to 0 when the x are big. So all that we use here is that in observation 1, in one dimension,
That's what we see in the side. The x should replace the side.
X should be sine. In one dimension, like I'm using if f of x is the characteristic function of the interval minus half, then the Fourier transform of psi is this sine pi psi over pi. This is one of the basic examples. So this is a pair of, this is a Fourier transform pairs. Sometimes we talk about Fourier transform pairs. As you see, Fourier transform essentially gives the function back. If you apply the Fourier transform 4 times, you get back to the original function. If you apply 2 times, you get just to the symmetric version of it. So the characteristic function of an interval in this function, sine pi c over pi c, or it's a Fourier transform pair. So it's nice. So this function here goes to 0 as c goes to infinity. Because the numerator is sine of somebody, keeps bounded by 1, and the denominator is 1 over pi c. I should make a few comments about this function. So this is a very nice example. Obviously, the function sine of x over x, you don't have a singularity at 0. Okay, you can say, oh, what about the denominator 0? No, the singularity at 0 is cancelled, right? So the value of this function at 0 is how much? 1. Sine x over x, when x is 0, the value is it's 1. So it is a continuous function, but you should pay attention that this function is not integrable. Okay? So the Fourier transform of a integrable function, this is an integrable function, but this Fourier transform is not integrable. But it is continuous, it goes to 0 at infinity, oscillating, but it goes to 0, but it's not integrable. It's not absolutely integrable. Okay, so the Fourier transform, so this is a basic example that shows that the Fourier transform does not map into L1. So Fourier transform of an L1 function is not necessarily an L1 function. It's continuous, vanishes at infinity, but it's not necessarily integrable. Yeah. So you start to think about, okay, if my function, if the Fourier transform were integrable, if it had some better decay, then my original function should have some smoothness. This function doesn't have smoothness. It is a characteristic function that breaks. So it's not even a continuous function. So this is why this function doesn't have too much decay. But still has some decay. Okay. So this is a very nice, very interesting, powerful, very beautiful lemma, I think, that illustrates a bunch of techniques that I hope by now you guys are getting the touch for it. The Riemann-Lebesgue lemma. You start to understand how cancellation takes place, how the oscillation kicks in here. If you have an integrable function, the Fourier transform is a continuous function, it goes to 0 at infinity. It is actually an interesting problem, and as far as I know, as far as I'm concerned, it's not yet completely solved to actually see. One can prove that the Fourier transform maps L1 into this space, but this is not a surjective map. I mean, not all functions that are continuous and go to 0 to infinity are Fourier transforms of somebody who's integral. That's actually an interesting problem to actually understand what sort of subspace of this guy is the image of the Fourier transform of L1 function. It's not a very easy problem though. Okay, good. Let's move on. Okay, so at this point, perhaps I should show you some Fourier transform pairs. Okay, so this is an example of a Fourier transform pair. Like that. Now you know how to do the Fourier transform of characteristic function of an interval. It's a sine pi x over pi x. If you just take this interval and dilate it, you know how the Fourier transform behaves. If you just change this interval to be from being centered at the origin and you put centered at another point, if you just translate the interval, Fourier transform will just be modulated by a character. So you know, essentially what I'm telling you is that if you do products of intervals, you get rectangles. You should know how to compute the exact Fourier transform of a rectangle, whatever he is in the space. Okay, good. This is one example that you guys should know. Okay, some other examples. One example that you should have in mind if you are going to tell people that you have studied the Fourier transform is you should know the Fourier transform of the Gaussian. Okay? So, if your function f of x is e to the minus pi lambda x squared, then the Fourier transform of a Gaussian is essentially a Gaussian. And this is just, let's say 1 over lambda 2 e to the minus pi c squared over lambda. So when lambda is equal to 1, it is an eigenvector. Okay, so this is the first example of a function e to the minus pi x squared, this is Gaussian, e to the minus pi x squared is a function that remains untouched via the Fourier transform. So if the parameter lambda here, it is just any positive parameter. If you set it to 1, then you're going to have an eigenvector. F hat will be just itself. And then you could in principle construct, if you know how to do it for lambda equals 1, you know what to do for any lambda by just a dilation in the variable x. So essentially, to prove this, it's just enough to prove for lambda equals 1 by dilation. Okay, and again, it's actually enough to prove for dimension b equals 1, because the Gaussian, when you do e to the minus 2 pi I xy e to the minus x squared, this will split in the product of the integrals. So what you want at the end is just e to the minus 2 pi I xc, let's say from minus infinity to infinity, e to the minus pi x squared dx. I suppose this is an integral you learned how to compute when you did your calculus class. So the idea is just to complete the square on the top. So this would be equal to the e to the minus pi lambda square. Right? And then you got here the integral minus infinity to infinity of e to the minus, how would I write this? There's an I here. So I actually want, let's say, square root of pi, or no, maybe just pi. I want x minus I, sorry, this is minus IC squared dx. Is this correct? Maybe minus pi and then a plus. Let's see, minus pi x squared, then minus 2 pi I this, and the final term would be minus c squared minus pi plus pi c squared, and then minus will kill it. So this is equal to this integral. This is an integral that is taking place. So the integration is in x, c is fixed real number, so if c is right here, this integration is taking place over this line. So what you do is you use complex analysis to do a basic contour integration to transfer the integration that is taking place here on this line, bring it back to the original real line. Okay, so essentially you're going to do contour integration in a big rectangle. The integrals on these sides will be small. There are no poles involved, so this integral is just e to the minus pi c squared, and then the integral minus e to the minus pi y squared dy on the real line. And then this integral here is just 1. I was actually pleased when I first learned how to do this integral here in, I guess, second course of calculus, right? The integral of a Gaussian. This is one thing that you cannot do in one dimension. This function doesn't have a primitive very easily. You know, so the idea is to actually call this function, I don't know if you remember this, if you call this s.
Use polar coordinates.
Yes, you do s squared. And you work on say R2 of e to the minus pi, and then just call it x squared plus y squared, dx dy. So in R2, and then you use polar coordinates. I was very happy when I discovered this. Calculus 2 in Brazil, I don't know if you use polar coordinates. This is beautiful. Okay, so a few things to remember. Integral of e to the minus pi x squared, 1 over the real line. If you never proved, prove it using polar coordinates, using this very nice trick. Now, if you want to integrate a Gaussian, a one-dimensional Gaussian, by just using this little bit of contour integration here, you find that the integral of a Gaussian is a Gaussian by this thing. By the product, the integral of a Gaussian in d dimensions will just be, when I say the Gaussian, they say that, let's say, e to the minus pi x squared will be to e to the minus pi c squared. Now if you want to put the factor lambda here, that's okay. This is just dilating your x by square root of lambda x. And then the lambda will pop up. You do the dilation here on the other side, like we have proved in the proposition one that you guys will prove. Okay? All right. Nice thing to remember. As I told you, if you're going to say to somebody, if you're meeting a girl on a date and you say that you know the Fourier transform, this is, okay, she will ask you, okay, so what's the Fourier transform of the Gaussian? And then so you're not ashamed to say the Fourier transform of the Gaussian is the Gaussian itself. Okay? Good. What, you guys never do this? When you take a girl on a date, brag that you know about the Fourier transform and know some mathematics and just show all your knowledge? That's a very powerful weapon.
Actually, I remember this trick of using polar coordinates because of something related to something like that.
Good. Good memories, you know. I'm glad that analysis brings you good memories. So another one for you to keep in mind, since you already know Fourier transform of characteristic functions of integrals, Fourier transform of the Gaussian, perhaps you should also know the Fourier transform of the exponential. The Fourier transform of the exponential, and I'm going to write what the exponential is. So let f of x be e to the minus 2 pi lambda modulus of x. So let's just say, let me just call it here f lambda, and call here f lambda. So to emphasize that we have a parameter lambda. So let me just call f lambda here. So let f lambda be this function. So this is what I call an exponential. It will have the absolute value of x here, but not absolute value squared. But of course, this function will be decreasing and integrable. And you can actually multiply by any polynomial that will still be integrable. So you should expect that the Fourier transform is a C-infinity function. And actually it is. The Fourier transform of this guy is the following function. Then f lambda hat at the point c is just a d-dimensional constant, lambda over lambda squared plus c squared to the d plus 1 over 2, where this constant cd is just gamma of d plus 1 over 2 divided by pi. Good. And again, of course, lambda here is just parameter bigger than 0. So if we have an exponential of this type, e to the minus 2 pi lambda absolute value of x, the Fourier transform is this kernel here, called Poisson kernel. So this is called Poisson kernel. This thing here. This is called the Gauss kernel. This is called the Poisson kernel. So whenever you hear these words, Gauss kernel is this guy, Poisson kernel is this guy. Okay. And you have encountered these guys before. You didn't, haven't you?
Resolve this equation.
This is what? This is like an approximation of the identity, right? When lambda is 1, you have the shape for it. And if you want to change it, well, you already know that this is an approximation of the identity because of the property that we observed, right? So if I have this thing, if you have a function g, and if you baptize your function f, let's say lambda of x, it's just being g of lambda x, then you know that f lambda hat. So if you just dilate by x inside, the Fourier transform will do the following thing, g hat of c over lambda. So multiplication of lambda inside will divide by lambda, and also divide by 1 over lambda to the d. So you see what's going on? This is what we call the approximation of the identity. This is like an approximation of the identity. And this is exactly what's happening here. So your function f lambda is just this original function, this e to the minus 2 pi x. Well, if you just change the parameter x by lambda x. So the Fourier transform is just a suitable approximation of the identity with the parameter lambda here. The same thing here, but now instead of thinking of the parameter lambda, if you want to put together with x, you should put square root of lambda x. So this is why you have a square root of lambda to the d, and then c over square root of lambda squared. So this is really, we're going to use these facts later. Now, I sketched the proof of this thing here. How do you guys think we can prove this thing? This is tricky. This is not easy to prove, but the proof, I will perhaps assign you in the homework list. The idea of the proof is very nice. And this function is one example of a function that is subordinated to the Gaussian. You know, in nature, there are some functions that are, you know, the boss, let's say. The Gaussian is one of the big bosses of all functions in nature. So this function is subordinated to the Gaussian in the sense that there exists a measure such that, say, e to the minus. Again, if we want to know how to do the Fourier transform of this function, it suffices to do it for lambda equals 1 because of this, right? So you actually want the Fourier transform of this function minus 2 pi functions of x. As I'm telling you, this function is under the control of the Gaussian, is subordinated to the Gaussian in the following sense. This function here can be written as a superposition of Gaussians, as an integral from 0 to infinity of certain Gaussians e to the minus pi lambda x squared against a certain measure d nu lambda. There exists a measure d nu lambda such that following identity holds. Okay? Then, once you have this identity in place, you will just plug in your definition of the Fourier transform and use Fubini.
But we have lambda to be 1.
Well, it's a different lambda. This is other. Call it t if you want. Okay. So once you have this in place, so if this function is, we call it f of x, then f hat of c will just be the integral. So if this function is the sum of some Gaussians, let's just call it the sum with of some Gaussians, the Fourier transform will be the sums of the Fourier transforms, because it's linear. So you can just prove that this is just going to be equal to 1 to the t d over 2 e to the minus p c squared over p under the same measure. So the difficulty is actually find such a measure.
Gaussian measure.
No, it is not. I mean, how would I describe this? Where does this come from? I'm trying to. It's not the Gauss measure. It's not just anything related to this thing. It's let's see. If we were to find such a measure, how would that be? So you want to write this guy as a superposition of Gaussians. I'm trying to think about. How would we find this? I'm not sure. I'm not sure there's a. I was trying to remember a philosophical explanation for what this measure should be, but I don't remember right now. But I will put you as an exercise just to, well, at least prove that this is, if I give you what the measure is, it's just a matter of doing the computation and showing that the identity works. There is a reason for the measure to be what it is. And for some reason I don't recall right now. But some functions have this property, that they're the integrals of Gaussians against certain measures. for the sake of a better word, let's just call these functions Gaussian dominated or Gaussian subordinated. And there is a nice, this has been a problem that was studied a long time ago, which functions can be written as the integral of Gaussians against a certain, by the way, I should say it's a non-negative measure, right? It's a non-negative Borel measure. Which functions can be written as the integral of a Gaussian over a parameter against a certain non-negative measure. These functions are sometimes called completely monotonic functions. They have the property that if you start differentiating these functions, they would change the signs of the derivative. So if you start differentiating this function, let's just call it when x is bigger than 0. Minus 2 pi x. Yes, so if you start differentiating this function, every time you differentiate, you get a minus 2 pi x to the bottom. Right? So the function itself is positive, the derivative is negative, the second derivative is positive, the third derivative is negative, and so on. So whenever you find a function with this pattern, that the kth derivative has sign minus 1 to the k over the real numbers, this function is called completely monotonic. And there is a theorem that says that a function is the integral of a Gaussian against a negative measure, if and only if it is completely monotonic. It's a very nice theorem from the 30s, 40s. Okay. How are we doing time? Okay. I think we're about to finish our time today. Let me just finish with this basic multiplication formula. So, proposition. I'll finish with a very simple fact. This is called multiplication formula, which is if f and g belong to L1 of Rd, we have the integral of f of x, g hat of x, dx over Rd is equal to the integral of f hat of x, g of x, dx for Rd. So the integral of f g hat is the integral of f hat g. Okay, if f is in L1. We have seen that if both functions are integrable, then their Fourier transforms are bounded functions. So this integral is perfectly well defined. I'm integrating a function which is L1 with another function that is bounded, and L1. So the proof is simple. Just observe that both integrals are equal to, by Fubini, they are equal to the following expression. Just open up one of these things. It's going to be equal to the integral over Rd, of e to the minus 2 pi I x y, f of x, g of y, dx dy. Again, since f and g are both in L1, I'm integrating f of x, g of y, dx dy. This is absolutely integrable if I just ignore this guy, so I can just move the integrals as I want. If we do the integration in x first, you get this thing. If you do the integration in y first, you get this thing. They're both equal to this. Okay. So today we are started the definition and basic properties of the Fourier transform. Still, we're doing what we call L1 theory. So our functions, our initial functions, all live in L1. Next class, we're going to finish this L1 theory. I want to prove the inversion formula for functions in L1. And then we're going to move to the theory in L2 and talk a little bit about the Schwartz space of distributions and how the Fourier transform can be extended. This is what I plan to do, to finish on Friday. Thank you all today for the attention. We continue in the last classes on Friday at 4. Good.